has large numbers of pieces of equipment, Ethernet switches and transport, border network gateways, remote access servers, broadband remote access servers, metro and transport equipment in TDM and WDM, and edge routers. And in the core network, there's core routers and switches, and we have to take into account the number of router hops. And in fact, it turns out that today the network is quite inefficient. And if you go from one point on Earth to another point on Earth with a simple transaction over the internet, typically you'll cross 15 fibre transmission hops and go through 15 routers, and that all adds up. Then there's long haul and submarine optical WDM transport. There's a whole range of optical equipment, EDFAs, Raman amplifiers, transmit and receive units, and so on. I understand, by the way, that Raman was involved in IISC, so the fame of this institute spreads. TDM and WDM cross connects, optical add drop multiplexers, and so on. There's a huge number of pieces of equipment, and to give you an indication of the detail we go into in Green Touch, all of this equipment is taken into account in our modelling and analysis, and no piece of equipment goes untouched in terms of being scrutinised to work out whether it can make some contribution to improving the energy efficiency of the network. And then, of course, as I said, there's data centres. So one of the things we have to do in building this model and analysing the energy consumption in the network is, having identified all the pieces of equipment, is to understand what the energy consumption of each of those pieces of equipment is. And this gives some examples of the energy efficiency of a number of pieces of equipment. And we typically express the energy efficiency of a piece of equipment, as I have on the vertical axis here, as the energy per bit. So if you think about it, that's really a good way to express energy efficiency, because if you want to transmit data from one place to another, the amount of energy for each bit of data really is the fundamental limitation of the equipment. So the core router, as you can see there, typically uses about 10 nanojoules per bit. Every time you pass a bit of data through a router, and there are 15 of those on a typical hop from one point to another in the internet, you will consume about 10 nanojoules. Ethernet switches consume a little less, WDM transmitters and receivers less still, and so on. All the equipment on the left there is what we would call sub-wavelength equipment. That is, that it works on data in the electrical domain. Electronic data is dealt with core routers and Ethernet switches. On the right-hand side, we're talking about equipment in the optical domain, such as optical amplifiers and MEMS cross-connects. They're little switching devices. And because we have such a huge amount of data in a single fibre, and because these devices, such as optical amplifiers and MEMS devices, can carry huge amounts of data, the energy that those devices consume is shared by very, very many bits of data. So it turns out that in the optical domain, the efficiency in energy per bit is usually quite good. And it's the electronic devices, especially the big core routers, that tend to be the most energy hungry in terms of consuming energy per bit. So if you think about transferring a piece of data from one bit of data from one point on the planet to another point on the planet, you need to count all the pieces of equipment that it passes through in going from the source to destination, and you need to figure out the energy per bit in each one of them. And having done that, you can add up the total amount of energy per each bit of data and work out the total energy consumption of the network, and that's what we've been doing. So, as I said before, you have to take into account improvements. If you're going to do projections into the future, you need to think about what Moore's law will do for us. And these are some historical and projections of the energy efficiency of a number of items of equipment. The very top one is the router, approaching 20 nanojoules per bit. The second one, the grey one, is a packet switch, but not a full router. And the lower ones, and my friends in Bell Labs who produced this slide were not very clever, I don't think, in their colour choice, so it's hard to see, but the SDH switch, which is also brown, is the smaller one, and the OTN cross-connect is one below that. But the point here is what this slide shows is there are projected improvements out into the future. So even without Green Touch, there are certainly some improvements in energy efficiency. But I take you back to that very first slide I showed you, that even with these improvements in energy efficiency in business as usual through Moore's law, the total power consumption of the internet will grow. David Nielsen, who's going to be speaking in this conference tomorrow, has done some analysis of router energy efficiency trends, showing the energy per bit for various routers over a period of time. And a linear fit to this graph shows that maybe it's about 25% per annum. But actually, if you look closely at the data, and there's other more recent data that confirms this, the actual rate of improvement of routers is actually declining. So the Moore's law is slowing, and in addition to that, a lot of the early improvements in router design were through picking low-hanging fruit. It was easy for router designers in the early years to make big improvements, but as time goes on, it's getting harder and harder to do it. So I suspect that this slowing of the rate of improvement through Moore's law and design improvements, just simple, straightforward design improvements, is really is going to slow down. One can also look at the energy efficiency trends in transport, and this is some historical data that we put together in Melbourne. I rather enjoy this slide because it shows some remarkable things back in the early days. The first transatlantic, these are all, by the way, transatlantic systems, and the vertical axis is the energy per bit per 1,000 kilometres across the Atlantic, and the first transatlantic transmission was on a single pair of wires, a coaxial cable I think it was, which had a lot of capacitance, so it was very slow, and the Morse key, you had to be very slow with your Morse key. It used about 100 millijoules per bit, almost a joule per bit. The very early wireless systems with Marconi used kilowatts of power at a very low bit rate, and they had used a huge amount of energy per bit, totally impossible by today's standards. But you'll see further to the right that as we get to the more recent undersea cables, the coaxial cables, and then the green squares, which are optical with regenerators, and the latest ones optical with EDFAs, there's a fairly definite trend there of about 15% per annum improvement. But my colleagues in the undersea cable world are telling me that they think that they're starting to run out of improvements as well, and that this 15% per annum is going to slow. So let's now look at what the key contributors are to the network energy consumption and this gap between current practice and what we might be able to do if we think about fundamental limitations. And I'll try and put this factor of 1,000 into context. First I want to just show some data for the access network. As G pointed out earlier, the access network is the most energy inefficient part of the network today. And this is partly due to wireless, but as I'll show in a slide later on, even the more energy efficient access technologies dominate the energy consumption of the network. So this is data from a couple of years ago and doesn't include some recent developments in wireless, but certainly as you get up to 10 megabits per second per user, the power per user is quite large with technologies like WiMAX or LTE. Fibre to the node, I'm sorry the line is a bit hard to see, is fairly constant at about 12 watts per user. HFC, hybrid fibre coax networks, are reasonably low power, but then the power rises rapidly as we move to higher bit rates with some of the DOCSIS improvements these days are very energy inefficient because there's lots of electronic equipment in the field. And fibre to the premises PON networks down the bottom use less than 10 watts, and the key here is that fibre to the premises is really the greenest of all the technologies in terms of power per user, and if I convert this to energy per bit, it looks even better in terms of favouring the fibre to the premises at very high bit rates. So let me now go back to the overall picture, and this is the first slide that I showed you with a few extra data points, or a few extra curves included. Again, the top graph, the top line is the global electricity supply, about 10 to the 12 watts, and growing at about 3% per annum. The dotted red line is the total energy consumption, the total power consumption of the network with 2010 technology and no improvements, and the solid red line is the one with 15% improvements. And the bottom lines show the relative contributions of transport, the very bottom one, that's optical transport in the core of the network, routers and switches, the second diagonal line, and the passive optical network. And we've selected here the very best of all access technologies. So again, I want to stress that if you take wireless into account, which would be more dominant here in India than it would be in other parts of the world, then wireless will push the access network of part of the equation up. But the interesting point, and by the way, this projection into the future takes into account, assumes about 40% per annum access growth rate and about 10% per annum growth in user numbers, although that might be conservative. And in 2010, the total number of users of the internet was about 1.5 billion. I think some people are estimating it's going to grow much more rapidly than 10%. The important point here is you can see that today, down here on the left, the network energy consumption is dominated by the access networks, and that's certainly true if you include wireless as well. It totally dominates over the other, over the routers and switches and over the transport part of the network. But there's a natural thing about access networks like passive optical networks, in that the power is dominated by the user modem, and the power consumed by the user modem stays pretty much the same as the bit rate increases. And so over time we expect, even with current technology, that the energy or the power consumption of fixed line networks will stay pretty much the same, pretty much a flat line like I've shown here, because it's dominated by the user modem. If you take into account wireless, of course, it will go up.